All right, so hello and welcome to the OneClass live stream. My name is Joey. I'm going to be your chemistry teacher for this session. So what we're going to do first is if you're joining us for the first time, we're going through this kind of journey of verifying solutions for some frequently asked problems in both mathematics and in chemistry. And these kind of contain questions from ranging from in the secondary school level as well as also in the university and college level. Specifically, today I'm going to focus mostly on high school chemistry questions, basically any problems you would find in both the junior and the senior level. And if you're tuning in from the Ontario curriculum, it's anywhere from basically grade 9 science all the way up to grade 12 university level chemistry. So, with just a little bit about myself before we start. Again, my name is Joey. I'm currently an Ontario school educator. My teachable subjects are chemistry and music. However, I am a month away from grabbing my mathematics teachable as well. So, I have today about 10 questions for us within the next hour, and hopefully we'll get through all 10 problems for today, and I'll be able to explain kind of the solutions and what the one class solution has for us, and I'll be able to hopefully teach you the concepts behind those questions. So, without further ado, let's get started on today's problems. All right, so our first problem here is says name each ionic compound, and then you have a series of 6 compounds. So let's get started on these guys here first. So we know that each of them are ionic. So this is a good hint because if it was ionic or a molecular compound, the nomenclature of those compounds differ. So for any ionic substance, just a little review. Let me make sure my tablet works here. Okay. So I have, again, 6 ionic compounds here. So let me do number 1. And basically for ionic compounds, we know that ionic here is defined as a non-metal plus a metal, right? Non-metal plus metal. Or even a better definition of that is simply an electron transfer. There's going to be a cation and also an anion in our compound. So cation plus anion. Because we know that one element is giving their electrons away, and one of them will be accepting their electrons here. So we have an ionic compound here, and our first guy here is Mg3N2. So let's define this guy first. So let me use a different color. So I have Mg3N2. Let me bring up a periodic table to help us with naming our compounds here. So every time we have an ionic compound, what we can do is we can simply just find the names of these elements in our periodic table. So the naming for this first guy here, I would go to Mg here, and I would look at, okay, which element is this? And usually, for ionic compounds, our metal is going to be the first element that we have for our compound here. The first element here is usually our metal, and the second one is our non-metal here. So first one's magnesium. So our metals are going to exist on the left side of the periodic table. So it's going to exist on this side here. So number 2 here, it says Mg. So we know that this here is magnesium. So you can write here magnesium. And we keep the name fully. And then the second one here is N here, which is going to be our non-metal. And as you can see, N here represents nitrogen. So we're going to write nitrogen here. But instead of writing the nitrogen like this, we're actually going to drop the OGEN, or the gen, and we're going to add IDE. So I'm going to erase some of this one, guys, and then write IDE. So it's going to become magnesium nitride. And this is the same thing, very similar for all ionic compounds. We basically write the metal as it should be, and then for the non-metal, we drop the ending and we add IDE for all ionic compounds. So in this case here, we have magnesium nitride, and this is going to be an answer for for the first guy here. For B here, we have Kf. So let's examine the first element here. We have K, which is going to be our metal. As you can see, K here represents potassium, right? So this here would be a potassium. And F here represents our nonmetal. So F here is going to exist on the right side of the periodic table. F here represents fluorine. Remember, we drop the ending and we add IDE. So fluorine becomes fluoride. So it's going to be potassium fluoride as our answer for this problem. That's C here. And then D here we have Li. Let's see. I don't know. This is LISE. LISE. I believe this is LISE. Yeah, D here's. Wait, I'm missing a C here. So I think this is L. Oh, C here is Na2O. Sorry. I think I got the order. So this is A. This is B here. This is C. And then this, I believe, is D. So I think C is Na2O here. So let me just erase this. So C is Na2O. And then I think D is LIS and E is CSF. So that's just a little formatting issue that they have, but that's okay. So C here we have Na2O. So again, Na is going to be my first element here, which is the metal. As you can see, Na exists on the left side of the periodic table, and this here represents sodium. And then O here is the oxygen. Remember, we drop the ending, so we drop the gen and we add IDE. So this would be sodium oxide. So oxygen becomes oxide here. D here we have, this is LIS. LIS. So we look at Li first, that's our first element. As you can see, this is lithium. Lithium. The S here, if I scroll a little bit to my right hand side here, as you can see, S here is sulfur. So again, I take the ending and I drop the ending and I add IDE. So again, sulfur becomes sulfide. So this is lithium sulfide. Finally, for E here we have CSF here. CSF, and then I believe F here we have Ki. So let me finish these two guys first. So CSF, I look at CS first, that's going to be the metal. CS here is cesium. I look down all the way up down to this here is row 6, and group 1. And this here is cesium. The F here we saw as before. F here we said it was fluorine here, and we drop the ending to get fluoride. So this is cesium fluoride. And then finally for Ki here we have K, which is we know as potassium. And the I here, if you look at our group 17 here, we know what the nonmetal I here is iodine. So we're going to drop the ending to make iodide. So potassium iodide. And these here are our solutions for question 1. So let's check their answers. So A here is magnesium nitride, which is good. B here is potassium fluoride. C is sodium oxide. D is lithium sulfide. E is cesium fluoride. And F here is potassium iodide. So this solution here is correct. All right, that's number 1. Question 2 is asking, describe the relationship between, and the A here is the radius of the cation and that of the atom from which it forms, and the radius of an anion and that of the atom which it forms. This is number 2. So this is the difference between atomic radius and ionic radius here. Atomic versus ionic radius. So let me take case A here first. And case A is asking us the radius of a cation and that of the atom from which it's formed. So let's look at some type of cation first. So a cation is going to be probably a metal, right? Because a metal is going to lose its electron to form a cation here. So let me take lithium, for example. So I have Li versus Li positive, right? So what I can do is I can draw the Bohr-Rutherford for both these atoms here. So Li, so for Li here, draw this guy here. In the first shell, I'm going to have 2 electrons. In the second shell, I'm going to have 1, right? And then for Li plus, it's very similar to this. Oh, sorry. In the first shell, I have 2. And then you realize in the second shell, I don't have an electron because I've given away this valence electron away to some type of nonmetal or whatnot. So in this case here, that is going to be my atomic radius. So let's compare our radiuses here. And as you can see, Li here has 1 more extra shell than Li plus, which means lithium is going to be bigger. So you can say that the radius between the atom, so this here is the atom, this here is the ion, this here is the ion would be smaller. So so therefore we can say that the cation formed. Remember, Li positive here is the cation. Cation form has smaller radius than atom from which it's formed, which it was formed from. So this here is the answer for question 1. So I'm taking lithium, for example. And then for case B here, we have the anion here. So let's take a look at case B. In case B, we'd have to actually look at a halogen or some type of non-metal here, because those are typically anions. So let's look at fluorine, for example. Fluorine here is F versus this would be F minus for the anion here. So I'm going to draw out my Bohr-Rutherford for F here. Okay, this is a very bad circle. I have the first shell, I have 2. In the second shell, I'm going to have 7, right? 1, 2, 3, 4, 5, 6, 7. And the F minus would simply just be F, but I would gain an electron, right? So it would be satisfied with the full shell. 1, 2, 1, 2, 3, 4, 5, 6, 7, and 8. And now this one is a little bit harder to see, but which one has a smaller radius, or which one would have a bigger radius? And in this case here, the anion formed. So let me backtrack here. So for cations here, we know that cations here form a smaller radius than this guy here because I'm basically losing a shell here, right? So this means that the cation here is slightly smaller than the atom which is formed. And we have this here is the anion here. So this one would be F minus. And then what we can do with F minus is we can look at both of these kind of Bohr-Rutherford diagrams here. And we can see that both of these guys are very, very similar, right? We have F minus here. We have F here, which has 2 shells. The first shell here is full, whereas the second shell here would be smaller. And then the second shell would be also full as well, or close to full, very, very close to full. It's again 7 electrons short. And then for F minus here, we also have 2 shells, right? Except the difference here is the second one here, the second shell is actually full as well. So in this case here for the anion, and now we're looking at, okay, what about the size of these ions here? So again, these positives, these positive anions here, we said that they were smaller in radius. And in this F minus here, these tend to be negative ions tend to be bigger than their neutral atoms here. So that's going to be our answer for this problem here. And anions here are going to be bigger than their respective neutral atoms. So cations are smaller and anions are going to be bigger. If you need help with this concept's really this concept is kind of talking about atomic radius and talking about ionic radius and how in terms of the periodic trends between those two properties there. So if you want more information about that, you can definitely take a look at, I believe I did a video already for OneClass talking about atomic radius and ionic radius, so you can definitely check that out as well. So let's look at this. And this is a typical trend here. So for example, specifically for fluorine, this one, fluorine actually doesn't follow this trend because because it has a full shell here, this tends to be actually smaller than the fluorine neutral atom. So in this case here, the fluorine actually doesn't follow the trend. But for example, if I had O minus versus O1 minus, or sorry, I have neutral oxygen versus 1 minus, then this would follow the trend here. So it really depends on whether or not it satisfies that full shell, because if it does satisfy that full shell here, it tends to be a little bit smaller due to the shielding and the effective nuclear charge of the atom. So in this case here, this specific case, the anion's actually smaller because it has a full shell, but typically in anions here, oxygen and like O minus, 1 minus, for example, are going to be bigger. So I'm going to say typically. So let me rephrase this. That means I didn't do the greatest example with fluorine. I should have picked another non-metal here. That's okay. So let's say typically. Anions have bigger radius, radii, than their neutral counterparts. That's going to be the answer for this problem here. So as you can see here, the A here says the radius of the cation is much smaller than the corresponding neutral atom, which is good. So we said it was smaller radius. And B here, the radius of an anion is much larger than the corresponding neutral atom. So I said it was larger, which is good. However, again, there's actually exceptions to this rule when it comes to having a full octet. And you explore more of that kind of when we're talking about atomic radius and shielding effect and effective nuclear charge, because in a full shell, like what we have here, for F minus, these electrons are actually very much attracted to the positive core in the nucleus. So it's actually going to tend to pull towards the nucleus, making actually the atomic radius smaller. So in this case here, its solution here is correct. But there are exceptions to this trend, specifically yeah. So I'm going to say solution is correct. Again, this is in general. We're talking about a general trend here. Okay. Number 3 says the solubility of copper 1 chloride is 3.91 milligrams per 100 milliliters of solution. Calculate the KSP. So let me look at the problem here. Maybe it'll give us some more information about this problem that this solution doesn't give us here. No, it does not. So that's okay. So we want the KSP of copper 1 chloride. Okay. So we have Cu, Cl, and this is going to dissolve into C1 plus Cl minus, right? 1 minus. And we have 3.91 milligrams per 100 milliliters of solution here. So what we're given here is we're given mass and we're given volume. So what we want to do first is we want to calculate the amount of moles here, because we need to calculate the concentration of copper chloride. So let's do that. So if we have our mass here, which is 3.91 milligrams, and what we can do is we can actually change this to grams, right? So we're going to multiply by 1 over 1,000. And this would give us our unit in grams here. Remember, we're just dividing by 1,000. So 3.91 divided by 1,000 would give us 3.91 times 10 to the negative 3. This would now be in grams. And what we need now is we need the molar mass of copper chloride, and we can easily calculate that by looking at our periodic table. So molar mass here, we can look at the molar mass of copper, which is going to be 63.546 grams per mole, plus chlorine, which is 35.45. And this is going to equal, let me just take out my calculator. So we have 63.546 plus 35.45 gives us a value of 98.996. And now what we can do is we can solve for the moles, right? Because we know that the moles is simply just mass over molar mass. And we're given our mass, which is 3.91 times 10 to the negative 3 grams, divided by 98.996 grams per mole. And this will give us our moles of copper chloride. So this here is 3.91 times 10 to the negative 3 divided by 98.996. And this will give us a value of 0.3870. So let me just say 0.3871 moles. And then what we can do now is we can actually solve for our concentration, right? So we have moles here, and then what we can do is, because we have volume, which is going to be 100 milliliters, which equals, I can change this into liters by simply, again, dividing by 1,000. So 1 over 1,000. So this one would be 0.1 liters. So I can actually solve for my concentration here, which is simply just moles divided by our volume, right? So here's 0.3871 divided by 0.1 liters, which is going to give us 0.038, I believe. So 0.3871 divided by 0.1. This should give us, this gives us 3.871. Yeah, 3.871, not 0.03, sorry. This is 3.871, and this is here is capital M in molarity. And once we can do that, what we can do here with the concentration here is we can finally set up our ice table to solve for our KSP for copper chloride. So we can do that. So because this here is the concentration of copper chloride, we know that the mole to mole ratio here, we can look here, copper chloride and Cu1 plus and Cl1 minus also have the coefficients of 1 as well. So therefore, these guys also have 3.871 times, it also has, 0.3871 moles of copper and chlorine that are being produced in solution. So what we can do now is we can actually figure out our KSP value by simply looking at our ice table here. So because we're not given our KSP for our equilibrium reaction, that's going to be something that we're going to be solving for. So we can do that actually. So we can set up our KSP equation as KSP is going to equal basically the concentration of our products divided by the concentration of our reactants here. So concentration of products that we're making is Cu plus and Cl minus, and we're dividing by CuCl here. And this is going to equal, well, I know that because the moles are going to be the same for copper, chloride, and copper, and I know it's going to be the same, and they have the coefficient of 1 because, again, I don't have, there's no coefficients in front of the Cu and the Cl minus, so these exponents are all going to be 1. So what I can do now is I can simply just divide out the concentrations and to figure out my KSP here. And this would give us our solution for this problem. So as you can see, this solution here is incomplete here. They wrote out a balanced chemical equation, but I don't think they calculated anything else for this problem here. But that's about it for this problem. Let me just see if I can solve for this this guy here. So we have 0.3. I'm gonna have to actually use my ice table to solve for this problem as well, but this here would be the given KSP value for this guy. I'm just missing one step here. So if I had CuCl, Cu plus Cl minus plus, and I know that I was given my initial concentration would be 3.87871 for my copper chloride. And this here would be 0 and 0. So I would have 3.871 plus x, or sorry, minus x. Plus x, which would be 3.871 minus x, x and x here. And then now what we can do is we can solve for our KSP value. So this is simply just x squared divided by 3.871 minus x. And this here would give us the value for KSP if we knew the concentrations of Cu and Cl minus here. So again, I don't know about the solution because again it doesn't give us a solution here for this problem. So I'm going to say this here is again an incomplete solution. But if I was given my KSP table here, I could actually solve for this. I believe it's it gives us like 1.2 times 10 to the negative 6. So that would be the answer for this problem. But again, we don't have a complete solution here because this is not going to give us a complete solution. But this is kind of the steps in order to calculate this. So we're given mass here. What we can do here is we can calculate moles and whatnot, and then calculate our concentration as well. So that would give us, and we can set up our ice table to solve for our KSP here. So that's kind of the logic behind this problem here. So again, this solution here is incorrect because again I don't have a complete solution here. What we can do here is, if we finish this problem, what we can do here is, let's see, I have 3.91 of 98 grams here. Did I divide this correctly? Let me just see if I found the moles here correctly, just to make sure. Because I have a feeling that something is off, because that's an awfully big concentration divided by, I think I multiplied instead. 0, or sorry, this is 98.996. Ah, yes, that makes sense here. So I think I multiplied here. So this here is my bad. So I think I plugged in a multiplication operation in my calculator, and not a division. So this guy here is actually 3.9497 times 10 to the negative 5 moles, which means this guy here would be not that. It would give me 10 to the 4 for my concentration here. Let's look at that. So it would be, again, 3.9497 times 10 to the negative 5. And this one would give us, let's see, let me divide this by 0.1. So I get 3.9497 times 10 to the negative 4. This is in molarity now. And what we can do, we can actually solve for this problem. So let's solve for this problem here. And we know, so what we can do here is we have an ionic substance here. So our products here is going to be, this concentration is going to be basically negated. And we can say that this we're basically here dividing by 1. And we basically just care about the KSP expression based off the products here. So in this case here, we actually don't need to do an ice table. Or well, we do, but we don't really care about the initial products here. We just care about we don't care about the reactants. We care about the products here, which is simply just x squared. So I guess we do have to do an ice table. So we Cu1 plus, and this is Cu minus. This here is ICE. So we start with 0, and we're adding some type of x here to both of these guys. So we're gonna have x for chlorine and for copper chloride as well. And if we substitute our expression here, this here is going to be x squared, right, divided by 1. And we know that x here equals our concentration. So this here was our 3.9497 times 10 to the negative 4. So what we're going to have is we're going to have 3.9497 times 10 to the negative 4 squared. And then this here will give us our KSP value for this solution. So this is going to be, let me plug this into my calculator. This is 3.9497 times 10 to the negative 4 squared. We give us value of this is 1.56 times 10 to the negative 7. And this here is going to be our KSP for this solution. So this solution is incorrect. KSP calculated. So I'm just going to write down the steps but not do it. So it says we need to solve for the concentration of the copper 1 chloride solution by figuring out the moles of copper chloride. Using stoichiometry. Okay, and then able to figure out the concentration of copper and chlorine in solution. And related to the concentration of copper chloride. KSP is going to equal concentration of Cu plus times the concentration of Cl minus. And that's how we're going to solve for our copper chloride. So the solution here is, our KSP of copper chloride. So the solution here is incorrect because, again, I have a incomplete solution. Okay, that was number 3. Don't know if we're going to do 10 problems today, but that's okay. Let's look at number 4. It says, using the given data, determine the rate constant. So let's do this problem here. It says A plus 2B equals C plus D here. And we give it some trials and some concentrations and we're given some rates here. So let's see, I have A plus 2B yields C plus D. And then I want to solve for my K value here. So in order to solve this problem, again, I'm going to just simply verify the solution. So I can look here, write out the reaction, which is good. And what we can do is we can actually write out the rate equation. So R here equals K times, and then what we can do is we're multiplying simply the reactants here, which is simply just K times B here. And we can actually rewrite this as K times A, and B here is going to be squared because I have the I have 2 in the coefficient here as well. So I can actually write this as a 2. And I'm just looking at the solution here. And they are, what they're doing is they're substituting, again, one point versus another point and just using substitution. So let's do that. So let me write out the general equation first, and then we'll be able to solve for this using substitution. So this here, and they give it to us as M and N, but it really doesn't matter which kind of letters you use in this case. And what we're doing is we're simply just subbing in a point. So I believe they subbed in the first point. Yeah, they subbed in for the first, they subbed in the first point for equation 1. So this here is trial 1. So trial 1 says that the rate here is 0.0123 is going to equal K times A here, which is 0.260 to the power of M multiplied by 0.230 times the power of N here, which is kind of our first equation here. And then what they did was they actually calculated, they used the second equation here, and then they plugged in the exact same thing for the second equation. So I would get 0.0123 equals K times, this here is also 0.260 times M, and I have 0.460 as the power of N here. And what we can do is we can simply just calculate, our M and N values by simply looking at these two values here. So we can say here, what they're doing here is they're dividing both equations, simply just using substitution. Again, if rate equals rate here, then I can simply just equate these two equations together. And as you can see here, if they divided both equations together, they're going to get to the power of N equals 1. So this here is going, this here will equal 1, and M here is going to equal 2 for this problem as well. So what they're doing here is they're simply eliminating the M first to only solve for this N value. So you're going to get, so again, this basically everything here crosses out. So again, it's because 0.0123 divided by 0.123 is simply just 1. K divided by K is 1, and these two guys here is also 1. So you can think of it as this is 1 equals 0.230 divided by 4.60 would be, you can think of this as 2 to the power of N here. So dividing equation 2 by 1. So sorry, this is actually flipped here. So let me redraw this here, because we want the bigger number on top, so it gives us a positive exponent. So we're basically just using the rate law, and we're comparing the rates of one versus the other, and we can simply just use substitution to solve for our K value, and that's what we're doing here. So 4.60 N is 0.230 N. If you divide 4.60 and 230, you can get 2 to the power of N. So N here is going to equal 0, right? Because anything to the power of 0 is going to equal 1. So N here is going to be the power of 0. We can do the exact same thing to solve for M value, right? So we basically just look at our points again, and we could look at our A values here. And what we can do is we can actually write another equation for trial 3 here, which is I have 0.520 is going to equal 0.0492, sorry. 0.0492 is going to equal 0.52 K, sorry, times 0.520 to the power of M and I know n now, which is 0, right? So this is 0.230 to the power of n. And I can simply divide this by our first point here, or our second point here, or honestly any of these equations would work. So I'm going to write 0.260, or sorry, this is 0.0123 equal k times I have 0.260 and then this here is 0. For the sake of time, maybe I'll just divide it by 0.23 to get me a nice 1 value here. 230. And so this here is equation 3 divided by equation 1 here. So we're simply just taking these two rates and we're dividing them, right? So 0.0492 divided by 0.0123. This gives us a value of 4. The k's here cancel out. 0.52 divided by 0.260 is simply to the power of 2. The m stays here. And these two guys also cancel out. So m here is going to equal 2, and n here equals 0, right? So now what I can do is I can finally write my rate constant, right? I can say that the rate is equal to k times a here, which is to the power of m, which is 2, times b to the power of 0. So this here, again, anything to the power of 0 is going to be simply equal 1. So what I can do is I can actually simply just cross out b in our mathematically speaking, because anything to the power of 0 equals 1. So it's not dependent on the concentration of b here, which means the rate here is simply going to be k times a squared. And what we can do is we can actually sub in any of these points to figure out this problem here. So as you can see, what they did was they figured out, they plugged in this case here, they plugged in the first point to solve for our value here. So rate, again, is 0.0123 equals k times a here, which is 0.260 to the power of 2. And again, we don't really care about b here, because if I wrote b 0.230 to the power of 0, this here is going to give me simply just a 1. So I just care about these guys here. So I have 0.0123 times k, whatever 0.260 squared is going to give me 0.0676. And I can simply just divide both of these guys to figure out k, right? So k is simply 0.0123 divided by 0.0676, which would give us a value of 0.1819. And this here is going to be in molarities -2, second -2. And that's it should be positive 2 actually in this exponent here, because this guy here was squared. Oh no, it should be -2. Yeah, because I need to get molarity squared here. Or sorry, I need to get molarity to the power of molarities per second for rate. So let's see. I need to get this here would be a -1 as well. -1. Yes, would give me that. So this here would be the correct solution. 1.8 times 10 to the -1, or 0.0 or 0.1819. So this here is the correct solution for this problem. All right. So number 4. I'm pretty sure we might only actually get to do 5 problems today, because these are typically what you see in a grade 12 problem, or even in a university level problem with rates and whatnot. So it does take a little bit of time to figure out that. And same with this problem here. What we're gonna have to do is we're gonna have to actually look at the standard enthalpies of formation, and we're actually gonna have to calculate bond energies. So this one, again, it's very tedious. It takes us a lot of time to figure out this problem, just because it's, again, just very tedious, and we're basically repeating the same steps over and over again. So we're given these enthalpies here. So we have standard enthalpy of this, or let me write delta H here. So delta H of Ng is going to equal 472.7 kilojoules per mole. I have delta H of Hg is going to equal, this is 216.0 kilojoules per mole. And then finally I have NH3. This is going to equal -46, sorry. kilojoules per mole. So given the standard enthalpy of these guys here, we want to find the N bond H bond energy here. Nitrogen single bond into this hydrogen in ammonia here. So what they're doing here is they're actually going to write out the balanced chemical equation, which is great. So we can do that here. And so we have N2 plus H2 will give us NH3. So we have to add a 2 here to balance out that, and then we're going to have to add a 3 here to balance out that as well. So again, I have 2 nitrogens here, 6 hydrogens on this side, 2 nitrogens here, and 6 hydrogens on this side here. And what they're doing here is they're writing, what we can do to this equation here is you can actually divide everything by half, right? Because again, this is here for 2, this is for 2 ammonias, and this standard enthalpy is only for 1. So I can divide everything here by all the coefficients here by 2, right? So I'm going to have half NH2 plus 3 over 2H2 would give us 1 NH3. And we care about 1 NH3 because this is going to give us negative 46.1 kilojoules. So that's what they have in this first, in this kind of first step here. And we're given all of these guys here, right? We're given our N2, which is our N2 here is simply, this should be N2. I don't know why they have N here. But this is going to be half of 472.7 because again, the coefficient of half. So I'm going to have to multiply this by half. And or if this actually gives us N, then I don't know if it's actually N2 here. So I'm going to give them the benefit of the doubt and say that this here is N and not N2. So in this case here, I don't have to actually multiply by half because this is just only for 1 nitrogen, and we only have 1 nitrogen here. So I'm going to say that we're going to have, this is going to be our number for our equation here. So again, as you can see, N here is half of N2. So it's going to be negative 472 kilojoules per mole. And again, this here is going to be an exothermic reaction. So we're going to have to change the sign here to a negative. And then what we have here is we have H, so we're going to have to multiply this by 3 over 2. Or we're going to have to multiply this by 3, right? Because again, the 2's here cancel out, so we're left with 3 hydrogens. So we're going to have to multiply this guy here by 3 and flip the sign. And we're going to have to add all that up. So we're going to have this here would be negative 472.7 kilojoules per mole. Plus, and then I'm going to have multiplied this guy by 3 and flip the sign. So I have 3 times negative 216.0 kilojoules per mole. And then what we're going to have here is, and also have to add in the ammonia, obviously, which is negative 46.1 plus negative 46.1 kilojoules per mole. So this is going to equal, we're going to add up all the reactions together. So this is great. So what we have here is half NH2, 3 over 2, H2, N and 3 H's, sorry. It's going to yield ammonia, half and 3 over 2. So what we're left here is we're left with nitrogen and our 3 hydrogens and our ammonia here, which is exactly what we have here. So we simply just have to add up our enthalpies here. So simply like so, and we will get our solution here. So this is, so mathematically this is negative 472.7 minus, this would be 648 minus 46.1. And this will give us our enthalpy, or this will give us our delta H of our entire reaction. So this is 648 minus 46.1. This is giving us negative 1,166.8 kilojoules per mole. And this here is the delta H of this entire reaction, right? So for NH3, because remember this here was our reaction in the beginning. So we have NH3, and we want to figure out each bond energy with NH3, right? So again, with NH3, if you drew the Lewis structure, we recognize that NH3 has 3 NH bonds. And because this here is for the entire reaction of NH3, we actually have to divide this guy here by 3 to figure out the individual bond energy of one NH bond here. So I have the answer divided by 3, which is going to be negative 388.9, exactly what their solution here as well. This should be a negative here, 8.9 kilojoules per mole. So this solution is indeed correct. Good analysis. So I believe that's going to be the last problem for today. Unfortunately, I only went through 5 problems because, again, these problems are they do take up much more time because they are pretty tedious in terms of explaining the problem and in terms of how to actually approach these problems. But I'll continue in the next stream for these problems as well, and we'll go through more of these problems hopefully in the next hour or so. Again, thank you so much for watching. Again, my name is Joey. You can, if you like these videos, again, check me out on YouTube at youtube.com/OneClass, and you can access previous live streams as well as also future live streams on that link. Again, thank you so much for watching. Stay safe, stay healthy, and have a great day. Take care.